We're on to page 6 here. Special right triangles. So we're talking about right triangles that are special. And there's two types. One comes from an equilateral triangle, and one comes from a square. Now, you might correctly say, but Chris, or Mr. Erlin, there are no right angles here. How can these be right triangles? In each of these scenarios, what we're talking about is cutting these shapes in half such that we get the right triangles. Because this had been 90 degrees here, 90 degrees here, that makes this 45 and this 45. Because this had been a square, if this side were x, this side would be x. If we wanted to find what this thing is, we could do the Pythagorean theorem. X squared plus x squared equals question mark squared, so 2x squared equals question mark squared. Take the square root of both sides. This is the equivalent of 2 times x equals question mark. So the x's come out and we get x root 2 equals question mark. This will always be the scenario. So this is our first special right triangle. It describes a 45, 45, 90 special right triangle. And if we know that the leg is, I don't know, let's call it x, then both legs are x. And every single time, if this is a 45, 45, 90 triangle, the hypotenuse will be x times the square root of 2. Which means when I look at this example and I see that this side length is 8, this other leg must also be 8. And the hypotenuse must be that same number times root 2. So if this side length is 25, this side length, marked y, must also be 25. And this side length must be that same 25 with a root 2 stuck on it. This one's a little harder. If this is 19, this is supposed to be a root 2 thing. In other words, when I know this side, the leg is 25, I multiply times root 2 to get the hypotenuse. So if the hypotenuse were 19, that would mean this side has to be divided by root 2 from the hypotenuse. So that if I multiplied it by root 2, I'd get to 19. So this side must be 19 over root 2. And that way, if I were to multiply this by root 2, I would yield 19. Now, this isn't actually in simplified format. We would expect this to be rationalized, which would be 19 root 2 over 2. So the best answer for x would be 19 root 2 over 2, and the same for y. For the geometry A population, I would accept a decimal equivalent. Okay, 3690 triangle. So this is the second scenario. If we start with an equilateral triangle, we know that all three of these sides are the same length. And we know that all these angles are 60 degrees. But again, we need to end up with a right triangle. So if I were to drop an altitude, what we learned about isosceles triangles in the past, we know that in an isosceles triangle, which this is, any altitude also bisects the angle and bisects the base, forming a median. Therefore, the triangle that is produced by this is still 60, this is 90, this angle gets cut into 30, this is called a 30, 60, 90 triangle. And whereas this whole length used to be x, I'm going to say it was 2x just for our ease of use. If this was 2x, this has been cut in half, so this is now x. And if I did the same thing I were to do here, trying to find this this question mark, I would say x squared plus question mark squared is equal to 2x squared. And again, the whole 2x has been squared. So x squared plus question mark squared is equal to 4x squared because the 2 gets squared. Subtract 1x squared, I get question mark squared is equal to 3x squared. Square root both sides. Question mark is equal to square root of 3 times x. The x comes out and I get question mark is equal to x root 3. So in other words, in these special right triangles, 30, 60, 90s, if the shortest leg, the side opposite 30, is x, the hypotenuse will always be twice that, and this leg over here, the one opposite 60 degrees, will be x times the square root of 3. This is worth memorizing, certainly for this unit. Therefore, in this application, if the side opposite 30, if this is 60 and this is 90, that has to be 30. So if that side is 5, the hypotenuse, y, would be twice that, which is 10. And the side over here would be that same side, 5, times a root 3. Similarly, if the smallest side, opposite 30, is 14, the largest side of the hypotenuse would be double that, as 28, and the side length opposite 60 would be 14 root 3. If the hypotenuse were given to us, so that this is 32, we know that that's twice what we're supposed to see here. So if that's 32, this would be 32 over 2, which is 16. So x is 16, and once we get that side, we can multiply by root 3 to get the other leg. Similar environment here. If the hypotenuse is 46, the smallest side, opposite 30, would be half of that, which is 23, and then x would be 23 root 3. Here's that hard problem. Well, before we do this, let's do this one. So here we're given that the leg is 9 root 3. Well, if that's 9 root 3, then this must have been 9, so that when I multiply it by root 3, I get 9 root 3, which then lets me move to the hypotenuse of double 9, which is 18. So here's our hard scenario. What if this value is already given, and it's supposed to be something root 3? In other words, this is supposed to be x root 3, where this is x. So if I solve for x, I can divide by root 3. In other words, this part down here is equal to 20 divided by root 3. Again, that's not rationalized, so we should multiply by root 3 over root 3 and get 20 root 3 over 3. If that's this side, then the hypotenuse is double that, which would be 40 root 3 over 3. Note that we're only multiplying times the top, not the bottom as well. So the hypotenuse would be 40 over 3 root 3, and y would be 20 over 3 root 3. Okay, those are the notes from page 6, Special Right Triangles.